Good afternoon, everyone. So, the last interglacial is a period which has been slightly warmer than today, and reconstructions of temperature indicate that this warming was particularly pronounced in the mid-latitudes, and it seems that tropical temperatures have been slightly cooler than pre-industrial Holocene. But there might be also seasonality issues with some of these proxy records, because there is an issue with seasonality during the last interglacial, because it is quite well known that during summer in the northern hemisphere, insolation was higher than today. And these higher boreal summer insolation also affected the tropics. So if you are at a location in the tropical North Atlantic, such as here, you would have experienced higher summer insolation and lower winter insolation during the peak of the last interglacial. So, do we have proxy records that document changes in seasonality? And for the tropical oceans, yes, we have. We can use the aerogenitic skeleton of annually banded corals to analyze them for strontium-calcium delta-18 proxies. Strontium-calcium is a temperature proxy. Delta-18 is influenced by temperature as well as by seawater delta-18. And you can create reconstructions at monthly resolution of tropical sea surface temperatures for short snapshots. So what you see here is a coral record from the last interglacial, and you see a time window of about 20 years, and you see the temperature changes winter, summer, summer, and you can count the annual cycles. You can derive the amplitude of the annual sea surface temperature cycle. Unfortunately, there are not many of these studies available at the moment. There are some studies published more than 10 years ago from the tropical oceans, and many of these studies were just focused on one single dated coral and provide a snapshot of 10 or 20 years or so, because these well-preserved corals are difficult to find in the tropics, because in the tropics it's raining, and these last interglacial corals you often frequently find on elevated reef terraces, so on land, and they are altered by diagenesis, and so that's a problem. You see some of these studies here. There are more studies now coming out from the tropical Atlantic. One study from the Northern Caribbean Sea will be presented by Kristine DeLong in the next talk. I will take you to the island of Bonaire in the tropical South Atlantic, tropical Southern Caribbean Sea, where we generated during the past years a number of time windows for different time intervals of the last interglacial and reconstructed temperature seasonality. So Bonaire is located off the coast of Venezuela, and it's an extremely dry, so it's a semi-arid climate. So it's not as wet as the northern coast of South America. It's really dry. You see a lot of cactus growing there, but that's well or excellent for the preservation of our last interglacial corals, which are located on this reef flat, this uplifted reef flat. So this is the last interglacial terrace, which we dated to between 118 to 130 kilo years ago using uranium series dating. And on top, these boulders are Holocene coral boulders, also dated and analyzed, which provide our Holocene benchmark for the interpretation of the last interglacial coral records. So you can drill these corals and then analyze these corals, do X-radiographs, see the annual density banding, so the coral was growing from here, from the bottom to the top, and then we do this high-resolution analysis. Microsampling of these corals is quite an issue. It's complicated, but we are using Diploria strugosa brain corals, which have a very dense part of the skeleton, the so-called theca wall, and that's an advantage because it's not so easily altered by diagenesis. So we are really using the theca walls for microsampling, for geochemical analysis, and also for dating. And just to give you an example for the dating issues, we analyzed or we dated different skeletal elements, the dense theca walls, and also bulk samples containing also more soft or fragile skeletal elements. And you see all the filled symbols here are U-series ages on bulk samples. And some of them really deviate from a last interglacial age. But if you then analyze from the same corals just the thicker walls, you get ages which fall really within this last interglacial time interval between 130 to 118 kiloyears ago. So, having said that, it's possible to generate from these corals monthly resolved temperature reconstructions for the last interglacial as this one from the late last interglacial in the same quality as we can do that with modern corals from this southern Caribbean island. And as a benchmark, as a Holocene benchmark, we are looking for comparison on previous studies conducted by us, where we analyzed in Holocene boulders, these boulders which were lying on top of the last interglacial reef terraces, strontium, calcium, delta O18, and this gives us the benchmark for the interpretation of our last interglacial corals. So these are the last interglacial coral records, work more or less done by my PhD student Will Brokers, who is working with me in Bremen. And you see several time windows. Each time window is provided by a specific coral, which has been dated by U-series, and we have time windows from 6 years or 4 years up to 35 years. So we can then pick up the maximum summer value and the minimum winter value of a given year of the strontium-calcium temperature proxy to quantify the amplitude of sea surface temperature variability at that time. The results are displayed here as a bar chart, so shown at the amplitude in strontium-calcium derived sea surface temperature variability. And if we are starting in the modern world, this is the instrumental SST seasonality. This is the strontium-calcium seasonality derived from 3 modern corals. There are deviations, but their mean fairly well tracks the instrumental SST seasonality. Then we have Holocene records, which indicate an increase in SST seasonality. If you reach the mid-Holocene, there's an exceptional period over here. I'm not going to talk about that. But if we are then going to the last interglacial, you'll see that during the peak of the last interglacial, we had significantly higher SST seasonality compared to today. And we have an evolution from the early last interglacial with an SST seasonality similar to today, to the peak of the last interglacial about 125, 24 kiloyears ago, with higher seasonality, back to modern-like conditions during the late SST seasonality. And talking about numbers, modern SST seasonality is about 3 degrees, and during the peak of the last interglacial, the coral records indicate about 5 degrees, so a 2 degrees increase in SST seasonality compared to today. Delta O18 shows a similar pattern, although differences between strontium-calcium temperature seasonality and delta O18 seasonality are due to delta O18 seawater effects on the seasonal scale, so influences of hydrology at the water surface on the signal documented in the coral. So if we then display the coral-based SST seasonality results just as simple dots shown here and compare that to the insolation seasonality at the latitude of Bonaire, we see that the coral-derived SST seasonality fairly well documents or is following the insolation seasonality in the northern tropical Atlantic. And what is shown here are transient simulations using the Cosmos-coupled model of SST seasonality in the Southern Caribbean Sea. And especially for the last interglacial, there's a fairly well agreement between model-derived and coral-derived sea surface temperature seasonality. And this is actually the first time this has been demonstrated using a number of corals. So older studies just looked at one coral from this period maybe, and now we have an evolution of tropical Atlantic SST seasonality reconstructed from Bonaire corals. So the question is, insolation seasonality was increased in the last interglacial due to changes in the Earth orbit around the Sun. This is due at Bonaire due to higher summer insolation and lower winter insolation at that time. With the corals, it's it's somehow difficult to tell if these SST seasonality, this increase is due to winter warming or summer warming. I will talk about that later. But the model tells us, the transient climate model simulation tells us that the simulated increase in SST seasonality during the last interglacial in the southern Caribbean Sea is mainly due to summer warming. So, just to show you this, these are additional simulations using the Cosmos model generated by Paul Geertz, time slice simulations, which are consistent with the earlier transient simulations as well as the coral results. And just if you look at this map here, this is the simulated SST seasonality using Cosmos at 125K anomalies relative to pre-industrial. And this is just to demonstrate that the location Bonaire, according to the model, is quite a good location and representative for SST seasonality changes throughout large regions in the northern tropical Atlantic Ocean. So the question would be, do the corals tell us something about mean climate changes, mean temperature changes in the last interglacial? And that's a difficult issue. Corals are wonderful to document SST seasonality. With the absolute temperatures, here are the mean strontium calcium derived temperatures, and you see that different modern corals from the same reef show a large deviation in absolute strontium calcium temperatures. So, but if we take this as our modern benchmark, our error bar, we see that during the last interglacial, the coral strontium calcium temperature proxy does not indicate warmer temperatures than today. In particular, during the peak of the last interglacial, the coral strontium calcium proxy indicates cooler temperatures than today. And this seems to be similar to the Holocene results. So if you look at the Holocene corals, we see if we start in the present day, and reach the mid-Holocene, we see cooler conditions in the mid-Holocene in the southern Caribbean Sea in the northern tropical Atlantic. And for the peak of the last interglacial, there seems to be this seems to be part of an evolution of peak cooling around 125K and then going back to modern conditions here, but we definitely need more data points than these 8 or 9 data points to verify that. But these cooler conditions are consistent with recent reconstructions of tropical SSTs from marine sediment cores, which also indicate for the peak of the last interglacial, say for 125K, a slight cooling in the tropical areas. So the coral results confirm the sediment core derived temperature results of slight cooling during the peak of the last interglacial in the tropics. So to summarize the results regarding last interglacial tropical Atlantic SST from coral strontium calcium, so the SST seasonality in the tropical North Atlantic seems to be largely controlled by orbital insolation changes, and the coral results indicate an increased SST seasonality at 124 to 126K, and SST seasonality was similar to today during the early and the late last interglacial. Preliminary results regarding mean SST changes indicate lower than today mean SSTs at 126K during the peak of the last interglacial, and mean SSTs similar to today during the late last interglacial. Thank you.
Have you seen any difference in growth rates between the modern Holocene and less interglacial corals? The growth rate difference, that's probably, it can be also can have an effect on the strontium calcium eventually.
You're totally right. Then that growth rate changes are an issue if they are below a certain threshold, so below 6 millimeters per year or something like that, then they could lead to apparently cooler temperatures in the geochemical proxies. But all our corals, the Holocene and the modern corals, have growth rates higher than 6 millimeters per year. So the growth rates are on average 7 millimeters per year, 8 millimeters per year. And they are similar compared to the modern corals. So during the last interglacial, during the late Holocene, mid-Holocene, growth rates are all about at the same range. So there we can rule out this problem.
So thank you, Thomas, for giving us an introduction into corals. I'll try not to repeat too much, but to add on to the presentation we just saw. So I want to also acknowledge my collaborators, my PhD student. I'll show some of his modern work from Haiti, and then also Eleanor Martin and Derek Rosenthal, who I'm working with. They are climate model diagnosticians. So we talk a lot about what we see in the paleoclimate record versus what they see in the climate models. And I'm going to show some of the results from that work. And then also Fred Taylor, who is our coral field guru, and River Shin, who does our uranium thorium dates. So, sorry. Can y'all hear me fine? I'm a little shorter. So we're still in the Atlantic warm pool, and this particular area is very important. And there's a very nice article that was published in EOS just a couple weeks ago that really made me happy, because it talked about, the Atlantic warm pool is very important because so many people live in this region between Central America, the Caribbean, and North America, and we depend on what happens with weather and climate in this region. So it's very important to understand, climate-wise, what's going on in the Atlantic warm pool. So some of the things that we are seeing in the modern records is that we have varying increasing temperature trends throughout this region, where in the South Caribbean, we're seeing large increasing trends in temperature, whereas in the Northern Caribbean, that's starting to level off into the Gulf of Mexico, then increasing trends as we move back to the north. So this is not a homogeneous body of water. There's lots of variability throughout the region. It's also influenced by ENSO coming in from the Eastern Pacific, and the sea surface temperatures in the North Atlantic, and the related climate phenomenon of the Atlantic multi-decadal oscillation and the North Atlantic oscillation. We also are concerned with Saharan dust, and this is dust that's coming in off of Africa, and this dust makes its way all the way over to the Caribbean into the Gulf of Mexico. And climate-wise, you might be thinking, well, why do we care about dust? And that's because dust is linked to hurricanes. And when we have large dust events, we have less hurricanes. So understanding what's going on with the winds, with the ocean, is very important in this region, especially for the people who live there. So I'm not going to spend a whole lot of time talking about last interglacial. We've seen some great talks today talking about this time period. So I want to highlight that the reason why I'm looking at the last interglacial is because this could be a possible scenario for future climate change, particularly looking at higher sea levels and what happens to climate when we do have higher sea levels of 5 meters to 6 meters to 9 meters greater than today. And there's lots of great paleoclimate records out there that document these shifts. However, we don't have a lot of paleoclimate records that can document the seasonal variability, and like the work that Thomas just showed with corals was seasonal, but we also don't have a lot of records that show us that decadal to multi-decadal variability, and that's something we can get at with corals. So I'm using a coral archive just like Thomas, but I'm using a different species of coral. This is Cedastria sedaria. So this is a relatively slower growing coral than what you see of Diploria strigosa. However, it's a very dense coral. And if you look at calcification rates, they're very similar in how much skeleton they're putting down. This particular coral I'm looking at comes from the northern coast of Hispaniola. So it was collected from one of those raised last interglacial reef terraces. It's very well preserved, and this record spans 75 years. So, and it goes back to, the uranium thorium dates tells us this is from the earlier part of the last interglacial, 128,000 years ago. So for comparison, I'm going to use the work of my PhD student with microatolls in Haiti, which is just to the south of our location of this last interglacial reef. And at this particular site, we have 5 microatolls. I'm going to show you data from 3 of those today. These were corals that were uplifted after the 2010 earthquake in Haiti. And Fred Taylor went to Haiti and collected cross-sections out of these corals, and you can see x-rays of those cross-sections here on the bottom. And that's what we're going to use for our modern comparison. Our longest one I'm going to show today is 84 years long. So I have very similar records, 75 years and 84 years, that we can compare to each other. So before we can go in and do our reconstructions, we need to do calibration and verification experiments. And one of the things I really wanted to get at with our last interglacial corals was absolute temperature. We can do seasonality very well, but absolute temperature has been something that the coral community has not been able to get at very well. So this started with my work as a postdoc working in the Florida Keys at dry tortugas. So here we collected 3 different corals and conducted calibration and verification experiments at this location. The reason we went there is because we have good temperature records. So I have buoy records spanning 1992 to 2008, and I have historical data from Fort Jefferson that the U.S. Army occupied. So I have data from 1879 to 1907 to calibrate and verify my coral record. And this is unprecedented. I don't know anybody else who's been able to do this. So with this data, we were able to come up with our calibration equations. So I'm showing the equations here for both of those 2 intervals. So the first equation was aligned. The strontium-calcium variations were aligned to that local temperature record. The historical interval is not, so I just used a seasonal cycle, and that's what we typically do with fossil records anyways, because I wanted to get a fossil coral value. So, and with this reconstruction, I can also go in and calculate what my error of reconstruction is going to be. So for these corals, it's 0.64 degrees Celsius. So recently, this work has been expanded on by adding a 4th coral in dry tortugas. They get exactly the same equation. That includes the slope and the intercept. My student's work in Haiti, he has 2 corals that we've calibrated in the modern interval, and you'll see that his slope is right between the 2 slopes, or right below the 2 slopes there in dry tortugas, but they're all within error, so that's based on 2 corals, very similar y-intercepts. And then some exciting news that Ilse Kuffner published just a couple weeks ago from the Florida Keys. So this was an experiment that Ilse conducted where she put out small coral colonies at 3 locations in the Florida Keys. So up by Miami, down in Key Largo, and dry tortugas. Each one of these sites has a temperature logger. And the corals were stained once a year for 2 years. And then they went out and collected slabs from these corals and ran the strontium calcium. So we have in situ SST with stain lines with our coral strontium calcium values, and she found the exact same equation that I found in dry tortugas with my historical and modern SST data. So this leads us to start to have some confidence that we have a regionally robust calibration equation that we can use to do absolute temperature reconstructions. So at this point, we've also expanded this to other locations. So we have a record in progress up at Flower Garden Banks. We find the exact same equation there. The USGS is working in the Virgin Islands and Biscayne Bay. The equation works there. Haiti and Florida Keys that I've already mentioned. So now we have 43 corals from the Caribbean that are giving us the same transfer equation. So this leads me to have confidence that we have a very stable calibration for this particular coral species in the Caribbean. I will also note, since somebody asked the question about growth rates, one of the things Ilse did with this experiment was to look at the threshold of where we start to see coral growth and strontium calcium diverging as growth rates drop. And she got the number of 1.7 millimeters for Psittaceous sedaria. This is very similar to the number I got with my dry tortugas corals, that we start to see shifts below 2 millimeters. So that's the threshold we use to evaluate our corals to make sure we don't have any growth-related effects. So for the climate models, we're going to look at the CCSM3 simulations. We're going to look at the last interglacial, that's a 300-year-long span, the control interval, that's 270 years, with no greenhouse gases, and then the 20th century, that includes greenhouse gases. We're going to compare that to gridded data sets from the Hadley Center and from NOAA. So one of the things we see with looking at correlations with our site, that's the black dot on the northern coast of Hispaniola, in all of these reconstructions, is that this particular site is very representative of what we see in the Northern Caribbean and the Caribbean at large, but not in the Gulf of Mexico. So remember, the Atlantic whirlpool is not a homogeneous body of water. So one of the things so we've got this weaker correlations as we go throughout the Caribbean. So we also see that there's an SST bias in the model data, or the model output. And we see this throughout the Caribbean. And this is something the diagnosticians are trying to get at. So here's our reconstruction from Hispaniola. And what we can see looking at this is we have those nice seasonal cycles, but we also have decadal scale variability, and that's about 3 degrees Celsius, and also interannual variability of about 2.8 degrees Celsius. If we look at the spectral analysis of our last interglacial, the model runs, we see those significant peaks, about 4 years and 8 years. We see similar periodicities in our coral record as well. There's also a peak at 20 years, but due to the length of the record, that's not, at this point, there's just not enough record to really resolve that multi-decadal periodicity, even in my multi-taper analysis. So now comparing our Hispaniola coral with the modern coral record. So the modern coral is at the top, and the last interglacial coral is at the bottom. These are both scaled to the same temperature range. So one of the things that stands out is that our last interglacial coral has greater interannual variability and decadal variability. And one thing to note is that our modern coral is a faster growing coral than our last interglacial coral. So these differences are not due to growth rate or sampling. These are real. So this is very interesting that we have these differences. So to think of a warmer world where we have higher sea level, potentially we could be looking at greater decadal scale variability and interannual variability in the Northern Caribbean. So looking at the seasonal cycle, one of the things we do see is this bias between the models and the observations. We see this same seasonal cycle in our coral records as what we do in the climate models. However, we see that there's that shift is present as well. So this shift, the bias that was noticed between the models seems to be persisting between the two. So that's an interesting result to take back for the climate models. And then just to kind of summarize, and Thomas showed most of this data here, I've just thrown in our record here from Hispaniola in red. So we'll see the seasonal cycle there is slightly larger than modern. And again, looking at the Caribbean as a whole, and this is looking at the models from the last interglacial control. And I want to focus on the winter and summer seasons because that's what we resolve in the corals the best. So we don't expect to see homogeneous results throughout the Caribbean. The Northern Caribbean and Southern Caribbean should be behaving differently, and the models show us that. So the take-home message here would be we need more records. It would be great to have longer records if we can find them so that we can look at this decadal scale variability and interannual variability. One question that comes up is, was strontium calcium seawater during the last interglacial different than today? And going back and looking at Stoll's work, for the last interglacial, we shouldn't have that issue because the sea level was actually higher, so we don't have to worry about the weathering of carbonate platforms changing strontium calcium seawater. So I don't think that's a problem. So this gives me more confidence that we can do our absolute temperature reconstructions. We're seeing very similar temperatures from the modern to the last interglacial. But what we are seeing that's different is the decadal and interdecadal variability. And I'll stop there.
Thank you. I'll take us to a slightly different location on Earth, and I'd like to mention that most of the results I'll show today are from my postdoc, Alison Hartman. So, the Red Sea is a long, narrow water body connected to the open ocean at only one point down here. But basically, it spans 3 climate systems. In the south, it's affected, or it sees the tropical rain belt dominated by the monsoonal systems. In the north, humidity, precipitation is delivered through northern hemisphere westerlies. And of course, most of the Red Sea lies within this major yellow, as you see, desert, the Arabian Sahara desert belt. And essentially, we don't know a lot about the previous location of these climate systems. I mean, just hypothetically, you know, this rain belt from the tropics could have migrated north at some point. Northern hemisphere westerlies could have pushed their way into the south. And maybe even other climate systems played a role here, like tropical plumes from equatorial Atlantic. So all of these things are critical for our understanding of the climate evolution of this region. And another point to make is that the Red Sea, as I said, lies within this desert belt, this hyper-arid desert belt, which has no rain, absolutely. So no rain here. A really narrow catchment means that hardly any terrigenous material is inserted to the Red Sea directly. We might see, or we might think that terrigenous material arrives in the Red Sea or is deposited there through aeolian processes, i.e. dust from the Sahara. So in this project, what we aimed to do was to look at downcore records along this transect of the Red Sea and try and reconstruct the terrigenous provenance and sources of material coming into the Red Sea. But specifically, the northern sector of the Red Sea is more sensitive to these sorts of questions because we know fairly well that down in the south the tropics are quite active, the tropical rain belt. So today I want to focus on the northern sector of the Red Sea and specifically on 3 cores, KL23, Core 68, both in the North Red Sea, and Core 74 within the northern extension of the Gulf of Aqaba. And the monitoring of the terrigenous input to the Red Sea, in this case, is focusing on the inorganic elemental concentrations, and I'll be primarily talking about calcium and magnesium, as well as neodymium isotopes expressed as epsilon neodymium values, and that's it. This is a compilation, map compilation by Abu Khami et al. From 2013 of various source terrains along the Sahara, looking at epsilon neodymium and strontium isotope compositions. So focusing on the epsilon neodymium values in blue, you can see that there are certain, or a few sources, a few hotspots of terrigenous material coming out of the Sahara, but roughly speaking, these values can be said to range within -10 to -15 epsilon neodymium units. On the other hand, the direct exposed rocks around the Red Sea, the Arabian-Nubian shield, we have some mismatches between my Mac and the PC. So the Arabian-Nubian shield, this crustal rock exposed along the Red Sea, is characterized by epsilon neodymium of -0.5 to -2.5 units, quite different than the Sahara Desert. A third potential end member, potential source to the Red Sea of terrigenous material is the Arabian Peninsula, which is actually really poorly constrained at this point, probably with intermediate epsilon neodymium values, but we do know it does carry a high magnesium signal. So, as I said, I'm going to focus on the 3 cores from the northern Red Sea, and shifting to the results, what we're looking at are the epsilon neodymium values over the last 160,000 years, with sea level here down below just for reference. So the first thing you can see in this diagram is the clear spatial gradient between the south, the blue, KL23, the green, and the red core in the north Gulf of Aqaba. And this gradient is consistent throughout this record, except for a few specific points. For example, during stage 5E and during the last deglacial. Another thing to point out is that during glacial maxima, in stage 6 and stage 2, we see a clear shift of epsilon neodymium values towards low values. And going back to these designated source end member compositions, these downward shifts towards negative values seem to be consistent with a stronger input of Sahara dust during the glacial maxima. On the other hand, this excursion, I would say a violent excursion in this diagram, this excursion of epsilon neodymium values, really off the charts considering the baseline, shifts towards the Arabian-Nubian Shield end-member composition, the local signal. Now, I want to add another aspect, another perspective to this by adding the magnesium-calcium ratio. So epsilon neodymium in the same diagram appears up here, and now we're looking at magnesium-calcium ratios for the same cores along the, over the last 160,000 years. And again, a clear observation here can be that overall there's no change in magnesium-calcium for most of the time, except for this time, the last deglacial, the late glacial and deglacial, where we see a real spike in magnesium-calcium ratios. Plotting one against the other in this diagram, it's possible to see or to distill out the different end members. So, for example, I've just mentioned that the high epsilon neodymium values are associated with the local sources, the Arabian-Nubian Shield. In the bottom left part of this diagram, the Sahara end member is plotted here, and I've added to this diagram modern observations, dust observations collected today over the last few years in the northern part of the Red Sea in Eilat, and these values are plotted here. And they seem to be consistent or quite fit into the picture nicely, showing that the Sahara end member is really an influence here. And of course, I should say these dust samples are identified to come out of the Sahara, each and every one of them. The final end member on the right-hand side here, as we can see, is characterized by high magnesium-calcium ratios and is associated with the deglacial interval. And the question is, what does it represent? So again, moving or using modern observations, I'll give an example here of a mega dust storm that started its way in northern Arabia in September 2015, and over about a period of a week covered the Levant and the North Red Sea with a really heavy blanket of dust, probably the most significant dust storm over the last century. This is actually a picture of the dust storm from my house while it occurred compared to a clear day. So a significant dust storm coming out of Arabia. And when we analyzed this sample of this dust, it turns out that it falls right here. So high magnesium relative to the other dust storms and an epsilon neodymium value of about -7, -6. So given this result and other supporting evidence, we can be talking about a 3 end-member system here with Arabian-Nubian Shield samples with high epsilon neodymium values, the Sahara dust, and Arabian components which are high in magnesium. So putting it all into context now, if we start to discuss the results, first looking at stage 5e, what we see here is interpreted by us as an indication of local precipitation triggering local floods, local floods in the North Red Sea. And this isn't an isolated observation, because we do know from other studies that during this time, this region has seen wetness. For example, caves in Arabia, fluvial deposits in the Sahara, and even additional cave deposits and other fluvial deposits north of the Red Sea in the Negev Desert, despite the fact that the interglacial is characterized in the Levant as a hyper-arid interval. So, using models now, I'll superimpose here the precipitation anomaly for the last interglacial calculated by Herold and Lohmann. We can see this is it fits the picture. So we could argue that an intensification of the tropical monsoon, the African monsoon, is the explanation for this. But when we actually look at the numbers here, the blue is a bit misleading. When you actually take the numbers here and look at them, this model predicts in the North Red Sea an increase relative to today of about 5, 10, 20 millimeters of rain during the summer. And bear in mind that today there's absolutely no rain there, so we're really talking about a bit more than nothing compared to today. Okay, so no rain in the North Red Sea. In practical terms, I would suggest here that schematically we can accept that the African monsoon system did make some significant migration towards the north, but it probably couldn't trigger these, as I said, violent events of rain in the North Red Sea. Alternatively, we do know of climate events, of climate systems known as tropical plumes, which are basically packages of humidity that are delivered directly from the equatorial Atlantic and deposit huge amounts of rain, sometimes twice, 3 times, 4 times the annual precipitation is delivered over a period of a few hours, and this today is seen to trigger massive floods in this region. Moving forward to the glacial, we saw evidence for increased dust inputs from the Sahara in the main body of the Red Sea, while local sites in the margins of the Red Sea see the local signals. So essentially a stagnant system where the big atmospheric systems do deliver the dust, but this is smeared on the sides. During the last deglacial, we see evidence for what I would think is an enigmatic event here, enigmatic process of overwhelming signal of Arabian components delivered into the Red Sea. So to sum it up, I've said most of the conclusions, but we do see this evidence for really strong and extreme precipitation and flooding of the Red Sea, of the North Red Sea during stage 5e. And I would argue this is associated not with a northward migration of the monsoon, but rather with this tropical plume system that comes from the West Africa. And beyond the fact that we see additional dust pulses from the Sahara and Arabia during later stages, it is also interesting to note that these tropical plume, their intensification, maybe in intensity and also in frequency, these things, or this evidence isn't replicated during the last or the present interglacial, the Holocene. And with that, I'll leave you with the Red Sea sunset. Thank you.
I was wondering, in the sedimentation rates of your core, do you have an idea of the duration of that event during 5e?
Of the what?
The duration? Was it the whole section or just maybe a millennial scale event or something like that?
No. The dating is based on oxygen isotope stratigraphy mainly for that interval, and it's the signal is a full stage 5e signal. This shift towards the Arabian-Nubian shield.
Can you rule out any influence of the Mediterranean as a source for the rainfall that caused these stronger floods during MIS 5E in the northern Red Sea?
Yeah, so a tricky question, of course, or a tricky question to answer, but I did mention that north of the sector I was talking about, in the Levant, in the Dead Sea Basin, the Dead Sea is characterized, or it tells us about hyper-arid conditions that existed in the Levant. We do see a superposition during 5e of remnants of these wet pulses, but I would argue these are remnants of the southern incursions, and it's hard to think in that case that the big, massive precipitation made its way from the Mediterranean to the south because of this gradient.
So I'm moving a little bit north, and Adi was talking a little bit about the conditions in the Eastern Mediterranean or the Levant. I'm working with Steve Goldstein and Yochanan Kushner from Lamont, and with Moti Stein and Boaz Lazar from the Geological Survey of Israel and the Hebrew University. The modern climate in the Eastern Mediterranean is dictated by storm tracks, and due to this large precipitation gradient between Mediterranean rainfall and the desert belt. This region is very sensitive to droughts, and there are wetter and drier years. And the reason that we get wetter or drier years is because of maybe changes in the path of the storm tracks, or decrease or increase in the magnitude of these storms. Due to climate change, the Mediterranean, and in particular the Eastern Mediterranean, is drying and is expected to dry in the future. You can see here in red the decrease in precipitation in the region in the past decades. And the reason for the drying is not completely understood, but it is related to the expansion of the Hadley cells. And due to climate change, it is expected that the precipitation will decrease by 20% by the end of the century. But in addition to this extreme drying that is expected and already occurring, there are already observations and also some future forecasts of increase in flooding in this region, or increase in the intensification of rainfall events. So we expect that we will have less rainfall, but that will be more intense, and also some kind of southward shift. So what I will talk about today is what has happened during the most arid periods in the past, in order to try to understand any kind of future changes. And I will be using the Dead Sea deep drilling cores that was drilled in 2010 and 11 in a water depth of 300 meters. One of the reasons for drilling this core was paleoclimate reconstruction, because of the location of the Dead Sea is between the Mediterranean zone and the desert belt. It reflects the climate in these both zones and the relationship between these regions. The core covered 450 meters of sediments over 200,000 years. The age model is according to uranium, thorium, and C14, and is summarized in these studies. And what we see in general is that during glacials, when lake level is high, we precipitate aragonite. And during interglacials, when the lake level is low, you can see here in green, we get a lot of salt precipitating thick halite layers in these regions. And I will focus today on the last interglacial, one of the driest periods in this region. So this is a close-up on the marine isotope stage 5 section. This is specifically the end of marine isotope stage 5E. And in green are the halite layers. And what you can see here, that these are alternating halite layers with mud layers, and it's not a continuous salt layer, meaning we don't have just drying of the lake. We have alternating drier and wetter intervals in this time, and the wetter intervals are something that is similar to the modern climate. Here we can see the halite layers in gray. In the global context, this is marine isotope stage 5E, and I think it was already discussed a lot today how it was relatively high CO2, and it is a warm interval, and why it's a good analog. And you can see here the summer and winter insolation in 30 north. And now I will close up on this, on the last interglacial. So we see here the salt is precipitating between 130 and 116 approximately. And we were able to reconstruct according to the amount of the salt that we see here and the chemical composition of fluid inclusion in the salt and pore waters, that the runoff decreased to between 30 and 50% of the modern runoff. So we are talking about an average, and this is an average for this whole time interval. So this is significantly less water and less available water than what we see today during that time. But what I want to talk about today is where does the water come from during these most arid periods? And I will be using uranium-234 to 238 in order to identify the different water sources around the lake and see if we see any kind of hydrological shift or just shutting down of all of the systems or climate system around the region. Today the activity, this is the activity ratio of uranium-234 to 238 in the lake is around 1.5. And the residence time of uranium in the lake is around 300 years, meaning this is the time resolution that we are expected to see changes in the isotopic composition of uranium. The Jordan River was when I'm talking about today, so I'm talking about before 1964, before the diversion of the Jordan River. The ratio of uranium-234 to 238 in the Jordan River is also 1.5. And this is the main source into the Dead Sea and explains why the ratio in the Dead Sea is 1.5. Most of the uranium comes from the water sources around the lake. So this is what is dictating the ratio. But when we look at other sources around the Dead Sea, we see much lower ratios, and to whoever is not used to ratios of activity ratios of uranium-234 to 238, there is a big difference between 1.5 and 1.1 or 1.2. So these are completely different values, and they represent a different signature. So floods around the Dead Sea and the eastern catchment water sources around the Dead Sea, and this region is the drier part of the watershed. They contain lower ratios of uranium-234 to 238. So if we have any kind of an hydrological shift, a decrease in the Jordan River flux, or increase, or just if this stays the same, we will see a shift in the uranium isotopic composition ratio. So this is how it looks in the core during marine isotope stage 5E. This is the uranium-234 to 238 versus time. In gray, we see the halite layer. This is the Jordan River and some western catchment springs end member. So we get ratios that are above 1.5. And if you're looking at floods, or the floods in the desert, or the eastern catchment sources, which are also in the desert, we get much lower ratios. So if we look what happens from the beginning of marine stage 5E toward the end of this time interval, we start from the typical ratio of 1.5. Most of the time, this is the ratio in the Dead Sea. These analyses were done on the autogenic minerals, so it expresses the composition of the isotopic composition of the lake itself. And we can see here this decrease from 1.5 to around 1.5 during 1.1 during the last interglacial. These values are corrected to time, of course, and corrected to the detritus content in the samples. So we can conclude from what we have seen in this shift that there was a hydrological shift. The dry condition shows us that the Jordan River didn't flow much into the lake, and we get a relative increase in floods and sources from the desert belt into the lake itself. And this also fits what Adi was talking about, so everything fits together, I think. If we compare it to other regional records like the speleothemes, again in gray are the halite layer, this is age, and we have several speleotheme records. The Sorek Cave record here in red is located deep in the Mediterranean zone. This is the map, and with precipitation contours. And then we have the northern Negev and the southern Negev. The northern Negev today gets more precipitation than in the south. And when we look again what was going on during the last interglacial, we can see that, and I think Adi was mentioning this time interval according to one of the questions. So we see in the peak insolation, in the peak of the last interglacial, there is no salt precipitation. And the budgets shows us that during that time we get similar condition to the modern conditions. But you can see here in blue in the northern Negev, where we get more precipitation today, there is formation of speleothemes, but they stop around 120. And in 120, during the most arid interval, we have only formation of speleothems in the south. So again, here we see this shift of everything is shutting down in the north and in the Mediterranean zone, and something is becoming more active in the south. When we compare it to some climate models, these are the runs of the CCSM3 of the NCAR model. And what I want to emphasize today is this big difference between 125,000 years and 120, and I think it was also shown in the corals that Thomas was showing before, that there is a big difference between 125 and 120, and this is seen in the records, and also it is seen in the model, because the insolation and the orbital forcing are completely different. So here we see 125 run, precipitation 125 run, compared to the control run, which represent the pre-industrial conditions. And you can see here that there is an increase in precipitation, and this is attributed to both increase in summer and winter precipitation in the model. But when we look at the 120 run, and it's maybe hard to see the colors in this monitor, but here I'm showing only the winter precipitation in 120, and this run is not very different from today. And again, I think also Thomas was showing similar conditions in his SST mean reconstruction in another region, but that there are many similar characteristics between 120 and today. So we see here a slightly decrease in precipitation during that time, which explains the, and I'm reminding that the climate today is mainly winter storms and precipitations during winter. In the summer, there is no precipitation in the model during 120. But when we look at the fall precipitation during that time, this is 120, this is September, October, November precipitation. So there is a slightly increase in precipitation during the fall. This is a relative increase in the fall versus today. So as you know, the insolation curves, there are different conditions in the seasonality and in the distribution, and therefore the distribution of rainfall during the temporal distribution of rainfall during these times. And the explanation can be the change in the orbital forcing. You can see here that this is the insolation anomaly. It's compared to today, this is 30 north. So the peak of the insolation anomaly during 125 during the summer, but then in 120 it shifts toward the fall, and this explains why in the model we get more precipitation, relatively more precipitation in the fall. So if I will summarize, we have seen that in the Levant climate was extremely dry during the last interglacial and reflects changes in the winter storm tracks. But we see increase in flooding in the desert belt that occurs during the most arid periods. And we also have seen that the climate records and the models in this region is very sensitive to the insolation changes. Thanks.
I was just curious if you could quickly summarize what the dating is based on.
The date model? Yeah, it's uranium, thorium, and C14. Last interglacial is done by uranium, thorium, and by a correlation to the spelothem caves.
So, good afternoon, and first of all, I want to thank the organizers for providing me travel support and thereby giving me a chance to speak here and present the first results of my PhD thesis, which is founded by the German Science Foundation and the priority program of IODP. So, after previous talks dealt with the last interglacial, let's now move on to the older time slices, especially the marine isotope stage 11, which I will compare to the interglacials during 9E and 15. Marine isotope stage 11 is of great interest because it's often considered as a possible analog for the Holocene because of its similar orbital parameters, and also because of it has got similar CO2 levels to pre-industrial times. But in global, it was 1 to 2 degrees warmer, which led to the nearly molten or melted Greenland ice sheet, which lead to 6 to 13 meters higher sea level. Because of its duration of nearly 30,000 years and because of sometimes its extreme temperatures, it's often coined a super interglacial. But let's now move on to the oceans. And traditional traces like stable isotopes suggest that there was a strong overturning circulation, but nothing is known about the exact deep water mass pronouns. So the neodymium isotopes are ideally suited for that. All continental material, like is found in Greenland and Canada, is depleted in neodymium-143 and therefore is very unradiogenic, meaning it has got low epsilon neodymium values, while younger material is enriched in neodymium-143 and therefore it is more radiogenic. The continental signal is now imprinted into the oceans, and therefore different water masses can be distinguished. And here I present you a cross-section through the northwestern Atlantic, from the southern tip of Greenland all the way south through the Bahamas. And you can clearly distinguish the water masses that are coming from the south, like the Antarctic bottom water and the Antarctic intermediate water, which are more radiogenic compared to the North Atlantic deep water, which is flowing from the north to the south with more unradiogenic values, while the most negative values are found in the region of the Labrador Sea. The sediment core I'm using in my study is ODP site 1063, which is located at the Bermuda Rise in a water depth of about 4,500 meters. Currently, it is influenced by the North Atlantic deep water, but it's situated near the interface to Atlantic bottom water and therefore reacts sensitively to changes of the bottom water source. The neodymium isotopic signal of the bottom water is archived in the sediment in the form of coatings, which cover the particles with ferromanganese oxyhydroxides. And in the lab, these coatings are extracted from the sediment via also our recently published leaching method. The bulk sediment is treated with a weak leach solution. Afterwards, the neodymium is separated via column chromatography and eventually measured on a mass spectrometer. In addition, for quality control, we measure other leached elements to exclude any contaminations by, for example, detrital carbonates or volcanogenic material. So one of the well-known neodymium records is the one from Böhm et al., also from the Bermuda Rise, which I plot here in the bottom for the last 150,000 years on an inverse scale. You can see how it clearly co-varies with major climate swings, which is here represented by the stable oxygen isotopes of the North Grip ice core plotted on the top. The most radiogenic values are found during the peak glacials, while more unradiogenic values are found during the rest of the glacial, and especially during the interglacials of the Holocene and the Eemian. Here, radiogenic values mean that the water masses were coming from the south, while more unradiogenic values mean that the water masses were coming from the north. So now let's move on to the older time slices. On top, I show you the neodymium isotope record from the Bermuda Rise. And first for terminations 1 and 2, meaning for the Holocene and the Eemian, which I showed you on the previous slide. And now my new data for terminations 4, 5, and 7, meaning for the interglacials during stages 9, 11, and 15. In the middle and the bottom, I show you the stable carbon and oxygen isotopes of the same or a nearby sediment core. The change from a cold to a warm stage, as you can also see in the stable isotopes, is also represented in the neodymium isotopic record. That means during the peak glacials, relatively constant radiogenic values are recorded, while during the glacial terminations, these values shift to more unradiogenic ones, meaning there's a recurrent shift from southern salt waters to northern salt water masses during the glacial terminations. So now let's have a look at the individual interglacials. Here they are plotted on a common age scale where 0 is defined as the boundary between the cold and warm climate stages as defined by Lisicki and Ramo. Let's start here with the Holocene, followed by the Eemian, marine isotope stage 9E, 11C, and also 15E. In doing so, marine isotope stage 11C attracts attention because of its very unradiogenic values of about -17. And in contrast to the other interglacials, these values prevail for the whole interglacial for nearly 30,000 years. So, however, these values like -17 do not occur at the core site today. So where do these values come from? Let's have a look again at the map I showed you in the beginning. The most unradiogenic values which can be found in the region of the North Atlantic are the region of Canada and Greenland. Now, when the Greenland ice sheet melted, a wide area of freshly eroded material becomes available to finally get into the oceans. But a higher input of negative neodymium alone isn't enough. There must also have been a strong overturning circulation to bring this signal down to the sediment. This can either be achieved through an enhanced deepwater formation in the Labrador Sea or a stronger spread of the water mass across the North Atlantic to the ultimate deepwater formation sites, where it is finally incorporated into the water masses, which then flow southward to the sediment core. So because of its really extreme epsilon neodymium signature, and because this extreme signature lasted for nearly 30,000 years, and because of its, that means that there must have been a strong Atlantic meridional overturning circulation, the term superinterglacial may also apply for the deep western Atlantic circulation. So let's now summarize my talk. So there's a recurring pattern with water mass provenance change across the glacial terminations, while during the glacials, the southern source water masses prevailed and the northern source water masses replaced these during the glacial terminations. Also, marine isotope stage 11 stands out in the record as extreme unradiogenic values of as low as -17 are recorded, which prevail for nearly 30,000 years, meaning that there's a strong AMOC which is required, and there's a strong influence of the Labrador Sea region. Thank you very much.
I was just wondering if you tried to do the calculations of changing the North Atlantic deepwater end member more towards Labrador Sea, and if you changed it enough, would you not have to invoke more flow to the Bermuda site? Do you know what I mean?
Yes, I know what you mean.
Yeah.
I calculated a while ago, and I can't really remember, but there must have been a higher input alone isn't enough. So there must have been also a stronger contribution of the Labrador Sea. Yeah.
Okay. Could we go back to that summary diagram that you were showing? Yes. So it's a superinterglacial, if you compare it with stage 9E, it's a superinterglacial not because of the maximum value, the intensity of the value, but the duration.
Values,
the persistence of those values. Okay. you want to elaborate a little bit on this? Or?
Yeah. because all the other interglacials, they like show a drop at the towards the end of the interglacial to more values like they're found today at the core site. But like these very unradiogenic values indicate there must have been also these strong AMOC. And for a time for nearly 30,000 years, that's really extreme. Yeah.
I was wondering, in the present motion, in the modern ocean, NADW is actually made out of three main components, three different water masses that mix up and form the NADW. And each of them has a different neodymium isotopic composition. On the other hand, 1063 is a fairly deep site. It's below 4,000 meters. How would you explain Labrador water, or at least a higher component of Labrador water, getting that deep into the Atlantic basin?
Yeah, that must, first of all, you can have a more intensified Labrador deep water formation, but you can also have a stronger spread of the water masses across the North Atlantic, so that the water mass, these unradiogenic values are not only incorporated in the region of Labrador Sea, but also like that they are more flowing to the other deep water formation sites, more in the the other regions of the Atlantic, and there they can also be incorporated into the water mass and when they finally sink down.
For me, it's strange to see 5E being less unradiogenic, because I think that during 5E, one possibility is that all the deep water formation is formed in the Nordic seas, and this is you should have maybe more unradiogenic.
Yeah, but maybe that's also because of the resolution of the record. Maybe there's just some values missing. If I remember correctly, between these last value here and the first one here, there's about 20 centimeters of sediment left. So maybe there's 1 or 2 samples missing.
Oh, okay. So, thank you.
I'd like to start off by acknowledging my co-authors. I forgot to put their affiliations on this slide, so it looks like I'm raising them to higher powers. And that's kind of appropriate because a lot of this work really it owes itself to the pioneering cave exploration and sample collection efforts of Derek Ford and Bernard L'Oreal in the 1970s and 80s. And I also want to acknowledge Jeremy Shakin and his former master's student, Nikki Beller, at Boston College, and Celeste Gambino, who's been doing the uranium-lead dating. So permafrost, or permanently frozen ground, covers large parts of the Arctic, and this study simply asks the question of whether there have been different amounts of permafrost thawing in past interglacials. So we know the kind of global scale and local radiative forcings fairly well. Were there differences in how much of the Arctic was covered by permafrost during these past interglacials that we see so nicely in so many paleo records? This isn't one of the reasons for asking this question. That it's very hard to know exactly how permafrost responds to climate change. This is a plot of the modern extent of permafrost as simulated by a group of CMIP5 general circulation models. This is just 8 of them. In red is showing the modern extent of permafrost. You can see these huge differences in how much permafrost the models think the modern world should have. This is the observational data set down here. This is just 8 of them. The rest of them shown in this paper don't look much better. And as a result, they predict very different responses to 21st century warming. So these are all the different models. Under a moderate emissions scenario, they get something like 15 to 87% loss of permafrost under this scenario. And in part, this is because permafrost is of course, primarily reflecting mean annual temperature. That's what melts the ice. But there's several other things that come into play, including vegetation, thus ground albedo, how long ice and snow stick around during the spring, so seasonality of insolation, etc. One of the reasons for trying to understand the susceptibility of permafrost to climate change is that there's a lot of carbon locked up there that might get more susceptible to release to the atmosphere under a warming scenario or under a melting scenario. The recent IPCC report suggests something like 1,700 petagrams of carbon there, approximately equivalent to that held in soils in the rest of the world combined. And you'll notice that this figure, though it shows fluxes in the carbon cycle basically everywhere else, it doesn't even try to draw arrows in or out of this permafrost box, because we simply don't know that much about what these fluxes are, how we might be perturbing them, and what the susceptibility for perturbation is in the future. So just as we're asking a pretty simple question, we're taking a pretty simple approach to this. So the basic idea is that speleothems need liquid water to grow. So in a glacial environment, in a karst that underlies permafrost, a cave that underlies permafrost in a karst environment, you have frozen pore waters. You also have poorly developed vegetation on soil, and so not a lot of soil air CO2. In a warmer climate, you start to melt that permafrost. You get hydrological connectivity through the karst. You also have greater development of biomass on the soil, and therefore more corrosive soil waters. And all of these things lead to speleothem formation. And so the basic idea is to go back in time to caves that underlie permafrost and look to see when speleothems were forming there in the past. We're not the first group to do this. In fact, back in the 70s, this was done in some of the same caves we're going to be talking about today. They focused only on samples that were located very close to the cave entrances, and found that near the cave entrances, at least, most of the interglacials were typified by speleothem formation. But further back in the caves, they discovered extensive flowstones and speleothems, but that could not be dated by the techniques of the time. More recently, Anton Vax and Gideon Henderson's group has revisited this approach using a latitudinal transect of caves in Siberia. And so you can see at kind of high latitudes, but not up the Arctic Circle, you get speleothems forming in these caves basically every interglacial going back. But up at this northernmost cave, most of the dates were infinite, so he dated 15 samples. Only one is shown here because it's the others are greater than 500,000 years and therefore beyond the limit of uranium-thorium dating. They obtained one sample from MIS 11, this little sample here, which gave an age of 427 plus or minus 23,000 years, so consistent with the first half of MIS 11. And just showing the kind of the difficulty of some of this work or some of the subtleties in this fairly small sample. In this first pit that they dug just a little too far into the uranium-thorium infinite material and got this kind of strange age in the middle of MIS 12. So you really have to be very careful in sampling these very small layers of growth in these high-latitude caves to really get the signal. Now, this is a really interesting result, but of course it's only one stalagmite from one place, one cave in Siberia. But as we heard about very nicely in the last talk, this is not the only result suggesting that the high northern latitudes were very warm during MIS 11. So for example, the Lake E record from northern Siberia suggests that the mean temperature of the warmest month was approximately 4 to 5 degrees C warmer than present throughout MIS 11C. Also in Greenland, we have pollen records suggesting extensive development of seed-bearing plants in southern Greenland. Also detrital sediment records suggesting widespread melting of the Greenland ice sheet. Based upon this record from these sites, they think that the ice sheet looked something like this, and thus contributed significantly to the estimated 6 to 13 meters of extra ocean that we had around during MIS 11. So now the question is, well, we have these interesting results from Greenland, from Siberia, what's going on in northwestern North America? So here's again the permafrost map for northwestern North America, showing the different types of permafrost going from greater than 90% down to kind of isolated permafrost. And we're working in three different sets of cave systems, each of which has 3 to 5 caves in it. So one set in the Yukon, one in the Nahanni province, and one at Crow's Nest Pass. This is 52 north, 61.5 north, and right at the Arctic Circle, 66.6 degrees north. So the Yukon, first of all, just to get rid of a first question, appears to have been unglaciated in the late Quaternary, so we don't have a history of ice sheet cover here. This is what the caves look like. So we see these obvious stalagmites here, but they're covered in ice. And you have these big ice plugs that develop in the backs of the caves as water vapor-rich air comes in summer, and then it basically is just a cold trap. It just freezes to the walls and to the existing cave formations in the winter, or when it hits this mean annual temperature air. But underneath this ice lies this thick flowstone, other cave decorations that points to wetter times. As we go further south to the Nahanni province, there's extensive limestone there, large ice caves, again with extensive flowstones, but no modern speleothem formation outside the very entrance of the cave. And then further south, we're to 52 north, we're getting fairly far south, but up at high elevations here in Crow's Nest Pass, again, these ice caves that are well decorated, but not with modern material, not with extensive modern material at least. So we have about something like 80 samples that we've gotten from Derek and Bernard that range from stalagmites to flowstones to stalactites, and we're basically just starting at the top and dating them to see when the most recent phase of growth is. As we get into the dating, I want to remind you just about the uranium-thorium system. So this is a simplified diagram, sort of ignoring 234, 238 disequilibrium that Yael was talking about, and just looking at the evolution of the activity ratio of thorium-230 to uranium-238 with time. And the thing that becomes obvious as you look at this graph, first of all, is why we have an infinite in uranium-thorium dating, is that the system comes to equilibrium after about 600,000 years, based on modern measurement uncertainties, and that small analytical uncertainties lead to much larger age uncertainties as we go further back in time. We're not used to 23,000-year uncertainties on uranium-thorium dates in the recent past, but that Vaxedol date is totally typical for 400,000 years because it's just hard to date once you get really close to secular equilibrium. So we, like Vax, found a lot of infinite samples. Roughly half of our samples are infinite, and I'll talk about that in just a minute. We have an initial date. We worked a lot to beat down our uncertainties, so sort of getting uncertainties to kind of orbital timescales. Here are all our dates, starting from the south, where we get most of the interglacials, and then clustering to earlier than 400,000 as we go further north, and we can just plot that up as probability distribution functions. And we see this clear peak, so these isolated ages from the southernmost sites during some recent interglacials, but this clear peak in MIS 11, and then this broad peak with larger age uncertainties in MIS 13 as well. As was talked about this morning, this doesn't have obvious correlation to any sort of global scale forcing, suggesting that it's something about redistributing heat in the climate system, perhaps related to AMOC, as was talked about last time. And then just to turn it around, because there's so much carbon in permafrost, if we do think that there was extensive permafrost melt in MIS 11, what impact might this have had on CO2 and methane? We don't see a clear difference in CO2 levels in these earlier interglacials, and in fact it's much lower here than in subsequent interglacials. So was it just released slowly enough that you had compensation and uptake by the ocean? And then just as a last thing, we're starting to move into uranium-lead dating to start to date those infinite samples. So as a test case, we took one that we had dated fairly well with uranium-thorium and took 7 aliquots for uranium-lead. Noah McLean helped us with the statistics of how to deal with the disequilibrium corrections for initial 230 and 234. We match our uranium-thorium age, and we're starting to march back in time using uranium-lead dating. So we've gotten some initial results going back to 1.5 million, but stay tuned as we start to build out that data set. And as we continue to do more uranium-thorium dating to really flesh out these PDFs and see which marine isotope stages are truly anomalous. But I think the preliminary results suggest that in these 3 regions, at least in the northern 2, MIS 11 appears to be typified in multiple caves by anomalous melting and speleothem formation. And the data also point to that there might be melting above the caves, especially at the Arctic Circle around the MIS 13. So with that, I'll thank you for your attention and take any questions.
I have two questions. One is if you can share with us roughly the initial delta 234 values, and second, if you thought about the mid-Pleistocene transition as a player in your results.
Yeah, so the initial delta 234 for many of the samples is close to 0, or it's close to 1. Some of them are up to 1.7, but actually in the 70s they noted that for many of these systems there's very little excess 234. The other question was about the mid-Pleistocene transition. Yeah, I think that the question that these results leave open is, was there extensive permafrost melting in basically every interglacial until MIS 11 and it stopped, or are these really anomalous? And that's the question we can't answer with the data we have right now. So I look forward to getting more data, I guess.
How do you explain the insolation at MIS 7 and the fact that you don't see the growth?
Yeah,
because it's not different from 5. It doesn't seem very different from 5, right?
Are you asking about? Just why we don't see melting during these high insolation phases like 5 and 7? Yeah, it may have to do with the fact that permafrost is seeing mean annual temperatures. That as you get a meter or more down into the soil, that annual cycle is damped, and so you're just mostly seeing mean annual temperatures. So unless that seasonality is rectified by extensive melting or by earlier melting of snow and some more absorption of that summer insolation, you might not see it. But I agree, it's surprising that we don't see a 5e peak, but it's what the data say. So.
Just wondering how much the size difference between the stage 11 and 13 peaks is due to the relative error.
Yeah, so most of that is due to the spread of errors rapidly as you approach infinite ages. We've done enough replication and we're pretty confident they're not infinite. This isn't just small analytical uncertainties giving us stuff that looks finite. But we're going to have to beat down those uncertainties to really be able to say something more. And so that one of the things I was getting at is that we're trying to move to analyzing larger and larger samples so we can get those tiny 230 and 234 beams on the Faraday cups, and that's how we move to a few thousand years error rather than 20,000 years errors.
So good afternoon, everybody. Now we are moving to marine sediments. And I'm going to present our relatively preliminary results for the MIS 15 from the Shackleton site. First, I'm going to introduce you the MIS 15 interglacial period. Here you have the oxygen isotopic record from the U1385 core. And if you want to know more details about this record, I recommend you to attend David Hodder's presentation tomorrow in the morning for the high resolution record. And here I have shaded the period compressed by the MIS 15. This is from around 600,000 years ago. This is a quite interesting and relevant period because, simulations performed by Jean and Berger predicts a minimum of Arctic sea ice cover and the maximum tree cover, in particular for the Western Mediterranean, for this interglacial over the last 800,000 years. The record we are presenting here is the first one, the first vegetation reconstruction for the Western Mediterranean, in general, because in Europe for the moment, but I think that the work is in progress in the Lake Ohrid in Albania. Only Tenagi Philippon is available for this period. And, for people not familiar with marine cores, they are a very good opportunity to correlate, in a direct way, terrestrial, sea, marine, and ice-related proxies, climatic proxies, and we can compare the dynamics in the different systems. For those who already don't know the study site is the IODP site 1385, the famous Shackleton site, and it's located on the southwestern Iberian margin of Portugal. It provides a 1.5 million year continuous record of marine and terrestrial climatic proxies. This area of the Iberian margin is a climatic crossroads where westerlies are relevant, but also subtropical ocean currents, and precession is particularly important here. So this is a site particularly well suited to study the millennial scale climatic variability over this part of the world. We have analyzed this record, and the chronology is was already published in this paper by David Hodel and co-authors, 2015. And what we have analyzed is pollen, that is a proxy for vegetation, but also for atmospheric conditions. And in particular, it provides important information about seasonality and the position of the westerlies over this region. I'm also presenting oxygen isotopic data from both from benthic and planktonic foraminifera, and they inform about ice volume and surface water conditions respectively. I'm also presenting a lower resolution record of alkanons as a proxy for sea surface temperature, and then the percentage of tetrad for freshwater pulses in the North Atlantic. So here you can see our pollen record for the MIS 15. I just finished to count the last samples, so it's I couldn't elaborate a lot on it, but you can appreciate that it's a quite high resolution one with approximately 400 years between samples and a standard deviation of 200 years. So now I'm going to explain a little bit to those non-paleobotanists which species are mostly involved in the summary curves. Here the main one, the most important one we use is the Mediterranean forest curve, where deciduous quercus, these are white oaks, are the most are contributing most to the sum. Also Mediterranean sclerophylls, that are a proxy for summer drought, are mostly composed of Quercus ilex, the evergreen tree, but also, for instance, at the beginning of the interglacial, there is a lot of olea, olive tree. And pioneer trees are mostly juniper, cupressaceae, but and also some betula. And steppe plants are mostly Artemisia, Chenopodiaceae, and ephedra. In several parts of the record, we can see some successional trends. Like, for instance, here we have this is the model. I'm going to show this as an example. We have a peak of steppe taxa, then pioneer trees spread, and finally the Mediterranean forest is taking over. Now this is a summary record with all the most important proxies we have considered, and to the left you have the vegetation record. Here Mediterranean forest in green, in orange the steppe taxa, and in red the Mediterranean sclerophylls. I know it's a bit confused, sorry, but I will try to show you the main details. Here are the heathlands, the heathers, sorry, that are also important as an indicator for seasonality. And then we have the marine data, the CO2 concentration from the Epica Dulce, and finally the orbital parameters. Now the first interesting point I would like to comment is that we have 3 major forest stages along this interglacial, and they are correlated with precession minima and consequently insolation maxima in the northern hemisphere. Out of the 3 forest, Mediterranean forest maxima, we have 2 of them that present maxima in Mediterranean sclerophylls, especially the first one, and they coincide with, they are synchronous with retreats in the ice volume. But there is the central one, where we have an increase in Mediterranean forest pollen, mostly deciduous oaks, because we don't have such a spread of Mediterranean sclerophylls. And this one is not related with changes in the ice volume. So now we are trying, in the next months or weeks, I hope, we are going to search for a plausible explanation for this vegetation pattern. Here, another important point to highlight is this retreat in Mediterranean forest that is not coupled with changes in the sea surface temperature and the conditions of the surface water, and also without increases in ice volume, relevant increases in ice volume. And we interpret this as a drier winter climate because of the increase in steppe taxa, but not in sclerophyllus, Mediterranean sclerophylls. And it coincides with a minimum in summer insolation. Then we move to another interesting episode here, that is a spread of Mediterranean forest coupled with headland expansion, but we don't have Mediterranean sclerophylls increasing in this period. Sorry. And how do we interpret this pattern of vegetation change? Well, it's synchronous with a precession maximum that indicates lower seasonality, and this is in good agreement with headland expansion, because at the moment headlands in the Iberian Peninsula are mostly located in close to the Atlantic, where the climate is much oceanic than farther inland. And there is also an increasing trend in obliquity that might be related to higher summer moisture availability. And then to conclude, I have highlighted, I have said it here, the most important periods of millennial variability in our record, and you can see that the Mediterranean forest pollen percentages are beautifully correlate with the planktonic isotopic record. So something is going on there, and now we are trying to refine our explanations. And the final. We have finally compared our data with modern simulations by Jean and Berger using LoftClim, and they used the orbital parameters for the MIS 15.1, but we have seen that in our data that the most important peak in Mediterranean forest corresponds to 15.3. So we have compared the results of the simulation with our data for both periods, and we see that they are much more similar to 15.3 than to 15.1. So we are now there is an obvious mismatch between the model results and our data, and we are going to search for an explanation. And to conclude, this is the first fine resolution direct glacial ice comparison for MIS 15 in Western Europe. Vegetation dynamics is proves a major proxy for seasonality, and in particular for moisture availability through time. Summer insolation is the main driver for Mediterranean forest development, more than ice volume, and the vegetation responded to both orbital and suborbital climatic variability. And then finally, the decoupling between data and model simulations, we have to find plausible explanations for it. So thank you very much for your attention.
You showed this increase in Mediterranean forest during stage 15-2. That was during a glacial maxima, ice volume maxima, and but at the same time, I think that was also during periods of high summer insolation. So
the first peak, you mean? Or?
The one, the 15-2 that you know if you go further back. Yep, this one.
This one. Yeah, here is where we don't have a good explanation at the moment, and it's the main question that we have.
But then it could be just driven by insolation, as you say.
Exactly. But we have to also see if other factors are intervening, biological factors. It's like at the beginning, perhaps competition or some other ecological processes are intervening to explain the mismatch with the models, because the orbital parameters, according to that, the insolation is maximum for the 15-1, and that's why the model shows the maximum tree cover for that period. Mm-hmm. But then our data show the contrary. So that's we have to. But yeah, you are right. It's our impression, but we have to discard, to rule out the other alternative explanations. Mm-hmm. Thanks.
Okay.
Just clarify something on this without trying to get into. I think this could be a slight problem of nomenclature here, because if you divide it into 15.1, 2, and 3, then you say there's a mismatch. If you actually divide into 5, as it's actually offered into substages, so what you're seeing, the place where there's a mismatch is 15C, which corresponds to an insolation maximum. The benthic record is not so clear. If you look at the Lysikian Raymo, they suggest that there is something there. We did not call that an interglacial. So going back to Eric Wolf's talk this morning, the two interglacials are 15A and 15E. 15C didn't quite make it to be an interglacial, but it's still a temperate period, and you have an increase in quercus. There's no mismatch. It's fine.
So, as we saw in this session, most of the paleoclimate research has been concentrated on the past 1 million years, a period dominated by the 100 kiloyears ice volume variations. And this is mainly because the sediment of this age is easily accessible by piston coring. However, this time period is difficult to test Milankovitch hypothesis because the response of the climate system to orbital forcing was highly nonlinear. Therefore, recent attention has been concentrated on the early Pleistocene, which was a period more clearly dominated by the 41 obliquity cycles. And as a complete understanding of the interglacial climate must also include the poorly known interglacials of the 41 kiloyear world, here we focus on marine isotopic stage 31. This stage is a key past interval, since it was demonstrated by proxy data and also model evidence its similarities with the future climate in terms of ice sheet configuration, global sea level, and temperature. This stage was characterized by a rare orbital configuration, high obliquity, high eccentricity, and pronounced minima in precession, which led to some of the highest summer insolation levels of the Pleistocene. And this strong orbital forcing, combined with relatively high concentrations of CO2, contributed to such a remarkable warmth in the high latitudes in both the northern and southern hemispheres that this stage has been described as a super interglacial. For example, in the well-known Russian Lake E, the pollen record and the estimated summer temperature and annual precipitation showed that this stage was much wetter than the Holocene and also than strong interglacials of the Quaternary, such as stage 5. However, the impact of this stage at lower latitudes remains poorly documented and understood in both terrestrial and marine environments. For instance, so far, in southern Europe, only 3 pollen records exist. However, the resolution remains low to detect in detail the millennial scale variability. So here we present a new high-resolution marine pollen record of stage 31 from the same site that César described in the previous presentation, the IODP site U1305. Located in the southwestern Iberian margin. This site is also known as the Shackleton site and covers the last 1.5 million years. Here we analyze the time period between stage 32 and the early stage 30, which includes the super interglacial stage 31. This record provides a unique reconstruction of atmospherical-driven vegetation changes that we directly compare with sea surface temperatures. And for that, we use a multi-proxy approach where we combine marine and terrestrial proxies in the same sample set. So while pollen analysis will give us the information on vegetation changes and terrestrial climate, marine biomarkers allow us to quantify the sea surface temperatures. Well, in terms of chronology, as the study interval is marked by one of the strongest precessional cycles of the Quaternary, here we use the precession tune time scale developed by David Odell and co-authors for this site, and that is based on the tuning of the sedimented lightness of this record with the precession. So moving to the results. So here I present the main results of our direct land-sea comparison. And from the bottom to the top of the graph, we have in dark green the arboreal taxa that are summer drought intolerant. Then in red, we have the Mediterranean taxa that reflect the seasonality of the Mediterranean climate. And in green, we have the temperated forest record that reflects moisturability and warm conditions in southwestern Iberia. Then in black, we have the sea surface temperatures, and on the top of the graph, we have the benthic record of our site, and also from the global stack of Lisecki and Rainbow. And so at orbital scale, we found a long forested period associated with relatively warm conditions in the Iberian margin, and this period lasted 34 kiloyears. This period corresponds to the terrestrial interglacial counterpart of stage 31 in southwestern Iberia, and we give it the name Sado. So, Sado interglacial is characterized by a moderate expansion of the temperated forest, reaching values maximum values up to 55%, a low development of Mediterranean taxa, and a particular development of summer drought intolerant taxa. And this type of vegetation indicates that this interglacial stands out in southwestern Iberia as a long interval of a temperate and humid climate regime marked by low seasonality. So, unlike the high latitudes, atmospheric and sea surface temperatures were not exceptionally high during stage 31. And these results are quite surprising, because southwestern Iberia is usually considered a region that is very sensitive to the precession forcing. So it was expected that the strong precession forcing and insolation forcing of stage 31 should lead to a very warm interglacial characterized by a high seasonality. So, but it was not the case. So this low seasonality of stage 31 must rely on other factors than precession. And in fact, when we compare our vegetation record with the orbital parameters, we can see that the temperate forest record is following the obliquity cycle rather than precession. And these results are also shown by the cross-correlation analysis that demonstrate that the forest record is not correlated to precession, but it is highly correlated to obliquity. And this dominant influence of obliquity on the forest development in southwestern Iberia during stage 31 is in line with the large evidence that shows an obliquity-first climate before 900 kiloyears. In addition to the long-term changes, our pollen record shows persistent suborbital climate variability throughout the studied interval that is revealed by 10 millennial scale forest decline events. And these events are characterized by a different character, amplitude, and duration. So, of the 10 forest decline events that were identified, 3 events, forest event 1, 9, and 10, these events are particularly long, cold, and dry. And they are also synchronous with strong drops in the SST. Moreover, they are associated with IRD events and the perturbation in the AMOC circulation, as demonstrated by the North Atlantic records. In addition, we also observed that these high-intensity events only occur once during the large ice volume conditions of the glacial stages and once the threshold of 3.5 per mil is reached. And these findings highlight that mechanisms related to high-latitude ice sheets dynamics are therefore critical to amplify the magnitude and the duration of the cooling events in southwestern Europe, and also during the 41 kiloyear world, and despite its reduced extent of ice sheets and the shorter duration of the glacials. In contrast to these events, the other events identified in our record, event 2 to event 8, they occur during the lower ice volume conditions of stage 31. And these events are characterized by less dry and less cold atmospheric conditions than the previous. Moreover, none of these events is associated to a SST cooling, ice rafting, or deep water perturbation on the deep water circulation. So, this air-sea thermal contrast at millennial time scale does not appear related to high-latitude ice sheet dynamics. Therefore, we performed spectral analysis to figure out what was the nature of this millennial scale variability. And this spectral analysis, the results of this analysis showed that these repeated atmospheric shifts in the atmosphere contain a significant suborbital variability at periods of 6 kiloyears, which can be related to the fourth harmonic of the precession component of the insolation forcing, the 5.5 cycles as identified by André Berger and co-authors in 2006. And this suggestion for a low-latitude insolation forcing is primarily because in the low latitudes, the incoming daily irradiation over a year is characterized by a double maximum, which leads to a larger thermal gradient. And this influences the atmospheric circulation and the humidity that is brought to southwestern Iberia by the westerlies. So we will have dry conditions in southwestern Iberia that will drive these forest decline events. So, to summarize, our study reveals for the first time that in contrast to the high latitudes in both hemispheres, in southwestern Iberia, atmospheric and sea surface temperatures were not exceptionally high in the context of other interglacials of the Quaternary. Instead, this warm stage stands out in southwestern Iberia as a temperate and humid climate regime marked by a low seasonality. And we find that this low seasonality is mainly due to the dominant influence of obliquity on the forest development rather than precession. In addition, our study reveals persistent millennial scale variability throughout the study interval. And moreover, we find that these events have a different signature in southwestern Europe that depends on the baseline climate states. So during large ice volume conditions, we will observe a land sea cooling that is related to the high latitude ice sheet dynamics. And in contrast, during lower ice volume conditions, we observe a land sea decoupling, and the dominant cyclicity of 6 kiloyears in the temperate forest allow us to associate these events with the fourth harmonic of the precession and therefore with the low latitude insolation forcing. Thank you. Gracias.
There are now quite a number of pollen data from this region for many interglacials, and I'm wondering to which most recent interglacial does stage 13 would be more similar, the most similar?
Just to be sure that I understand, which stage would be most similar in terms of forest development? For instance, I also analyzed stage 11, another super interglacial, and you can see it in my poster. It's 160. And this stage, for instance, stage 11, it was characterized by a very low insolation forcing. And I have the same percentages of temperated forest, of Mediterranean forest, than I have on stage 31, which is quite surprising given the difference in the orbital forcing. So, in fact, I would say that each interglacial is different, and we cannot, stage 31 proves that we cannot expect to have something just given, for instance, the orbital forcing.